So from set theory, the concept of Cartesian products is not new. So Cartesian products. So this borrows quite heavily from our knowledge on the XY axis, where we have the x-axis and the y-axis, and we normally give points on the Cartesian plane. We call this the Cartesian plane, and we give points in form of ordered pairs, x, y. And on the Cartesian plane, it is understood that when you give the coordinates of a point as x, y, it is understood that x is the x coordinate and y represent the y coordinates, or rather x. Now if you do this from set theory, x is a member of set x and y is a member of set y. So we can say that as a point, or rather points, points on the Cartesian plane, on a Cartesian plane, are usually read. They are usually read using rectangular coordinates, using the rectangular coordinate system. As a set of ordered pairs of this form, e.g. pairs of the form, say, AB. So we shall start, you see, when we read now coordinates of a point in the Cartesian plane, we normally understand that the first value is the x coordinate, the second value is the y coordinate. So we shall define an ordered pair. We start by defining an ordered pair. What do we mean by an ordered pair? And for this, we can say that an ordered pair, let me just have it at the top there. Definition, ordered pair. We can say that an ordered pair is a set containing, say, an ordered pair is a set containing exactly two elements, for which it has been decided, which is the first in the pair and which is the second in the pair. So it has been decided which is the first and which is the second. In that pair. And that is why I said the coordinates of a point, like if I take the coordinates of a point xy, it just comes automatically that I will know, this being the coordinates of a point, the first value is the x coordinate, the second value is the y coordinate. So in the Cartesian plane, the way that pair of coordinates is written has been decided that the first value in the pair will come from the x-axis and the second value will come from the y-axis. So when you have such sets containing of those pairs of points, then we call it an ordered pair. We call that an ordered pair which contains exactly two elements, and it is known the first one will come from this set, the second one will come from which set. Next, we define the Cartesian product of two sets. Another definition, we can say that the Cartesian product of two sets, say A and B, of two sets A and B, is the set of all ordered pairs, is the set of all ordered pairs. Now we know what an ordered pair is. All ordered pairs, say AB, where A belongs to set A and B belongs to set B. And we denote the Cartesian product and is denoted by A cross B. So that is what we call the Cartesian product of sets A and B. We denote it as A cross B. So symbolically, we can say that we can represent this as A cross B is equal to the set of points of the form A, B, such that A belongs to the set A and B belongs to the set B. So that collection of points, this one, represents the order, the Cartesian product of A and B. Then you will find that if, for example, we revise the order, if we reverse this order, let me continue up there. If we have the set, the Cartesian, if now we want the Cartesian product of B and A, B, the Cartesian product of A, B and A will be the set of ordered pairs BA. Note we have reversed the order now. BA such that B is from set A, is from set B. B comes from set B and A comes from set A. So again, you can see now this operation is not commutative. So you will find that in general, B cross A, because now these points may not be give the same results depending on how the operation or how the sets are defined. So we can say in general, the Cartesian product is not commutative. In general, A cross B is not always equal to B cross A. Because you can see, even the way we obtain their ordered pairs, it is different. When you reverse the order in which the two sets have been multiplied, you reverse the order in which the pairs of points will be obtained. For example, e.g., suppose we have two sets. Suppose the set A has elements 1, 2, 3, and B has elements A, B. Then we can have this set. Then the set A cross B, that is the Cartesian product of A and B, will consist of these pairs, these ordered pairs. They'll be in the form AB, where A is from A and B is from B. So we shall have these pairs, 1A, 1B, 2A. The first entry is from set A, the second is from set B. 2B, 3A, 3B. So that collection of points represents the Cartesian product of A and B. You can see throughout all the pairs, the first element is from set A and the second is from set B. But now, if, for example, we reverse that, to obtain the Cartesian product of B cross B and A. So B cross A will be the collection of these points. The first entry will, the first element in the pairs will come from B, and the second will come from A. So we shall have points of this kind. A1, A1, A2, A3, B1, B2, B3. So you can see now the pairs of points. These points in B, in the Cartesian product of B and A, are different from the points in the Cartesian products of A and B. And that is why we can now clearly see, even from this specific example, that A, the Cartesian product of A and B, is not equal to the Cartesian product of B and A. Those pairs of points are different. So that is now the Cartesian product as an operation. You can easily show that this is not commutative. So we can say that in general, we can say the Cartesian products in general, Cartesian products are not commutative. In general, Cartesian products are not commutative. And that's what we have shown. Next, we define the term, another terminology that is now a relation. We can say something about relations on sets. By relations here, we look at situations. Okay, in general, if you were to use a layman's language, a relation is there are some family ties or something of between two people. When you say that this person is related to the other person, then it means that there's some tie, something in common between them. So now, in sets of real numbers, the types of relations we look at are relations like those operations that relate two numbers, like equal to, less than, is the square root of, is the square of, etc. So those are the relations we talk about in as far as sets are concerned. We don't talk of now relatives like parents and sisters and siblings and friends. So I want to say something about relations here, but now this time with reference to sets or with reference to mathematics. Relations. So, in as far as families are concerned, a relation is a tie between some two people or some relation, just the same as the word suggests. But now in sets of real numbers, the types of relations we consider are, for example, say equal to, less than, greater than, maybe we can have a square of, or the squares, a square, a root, and so on. So those are the kind of relations we refer to when now we are in referring to sets in mathematics. So we can say that those relations that involve two elements are called binary relations. So we can also say that relations involving two elements are called binary relations. And no wonder when we are defining an algebraic system, we've always talked of a set together with a binary relation. But now when we are representing a relation per se in notation form, we normally represent them in form of pairs. We represent them in form of pairs, whereby the pairs, it is known that one the first element in the pair, where it comes from, and where the second element in that pair comes from. So we can consider this. For example, consider the set of integers. Consider the set of integers with relation with relation, let's say I'll put the relation in quotes here, is the square of. Is the square of. Using ordered pairs, such as, now if you were to represent that relation in ordered pairs of this kind, then we have this. The relation is the square of. This is the relation. Is the square of. So in ordered pairs, we shall have pairs like this, like 4, 2. 4 is the square of 2. We can have another pair, 4, negative 2. 4 is the square of negative 2. 36, 6. 36 is the square of 6. Also, we can have 36, negative 6. 36 is the square of negative 6, etc. So these pairs, all of them obey the relation that we are having. So the relation is the square of. So the first number is the square of the second one. So we can have this to indicate an integer and its square. To indicate an integer and its square. So we can now indicate this kind of relation in general as follows, whereby the first one is the square of the second. So we can say that this can be indicated by, in general, can be indicated by this ordered pair, n squared comma n. So that the first entry in the ordered pair is the square of n, and the second one is the n itself, where n is an integer. Where n is an integer. And we note that we can now see that since the squares of integers are also integers, then we find that these pairs, or those ordered pairs, belong to the set which is the Cartesian product of z cross z. So notice that this pair, n squared n belongs to z cross z, the Cartesian product of the set of integers by itself, whereby the first one is the square of z, the square of n is also another element of z, and n is an integer. So we find that relations are represented in form of ordered pairs. But now the rule that governs that relation must be stated or must be known. The rule is normally known, and then now you can generate ordered pairs that satisfy that rule. Another definition, let me just clear all. Another definition when we have a binary relation from a set A to a set B, that becomes a subset. It is actually a subset of the Cartesian product of A and B. So a binary relation from A to B is a subset of the Cartesian product. Now we know what the Cartesian product is, of the Cartesian product A cross B. And that's what that's why we have said that n squared n, the ordered pair n squared n, is we also found from the illustration we have found that the ordered pair n squared n is belongs to this Cartesian product of z cross z. So this is in agreement with what we have found from our example. Then now, some other terminology I want us to define in relation to, or in connection to relations. We can define now the domain and the range. You see now, this is where we are obtaining the set on which the relation is applied, the set where the relation is applied. So I want us to define some terminology there. We can say that the domain of a binary relation, the domain of a binary relation is the set of all the first elements. It is the set of all the first elements in the ordered pairs. In the ordered pairs. In the ordered pairs in the relation. In the relation. And the range, let me continue up there. And the range is the set of all the set of all the second elements in the ordered pairs. In the ordered pairs in the relation. So we can say that we can denote now the domain and the range as follows. We denote domain by D of R, where R is the relation, and the range we denote it by small r of R, where R is the relation. So we have the domain of R and the range of R. The domain is the set of all first elements in the ordered pairs of the relation, and the range is the set of all the second elements in the ordered pairs of that relation. For example, I hope the screens are still sharing. I'm seeing the numbers there. Is BSS, are you in? Are we having BSS and BMC? BSS and BMC on the public chat, let me know if you are there. Seeing 205, 205. BMC, BSS, because I shared this link to BSS as well. BSS, are you there? If they are not there, I'll follow up with their rep, wondering why they are not in this class. BSS. Okay, so let's continue. So we have the domain and the range of a relation. Then we can illustrate this with an example. If we consider two sets, say S and T, and we want to write down the Cartesian products of S and T, and then now from that Cartesian product, we shall also describe or define a relation on that set. On that set, a relation of a relation we shall define some relation. So let's consider. I want to illustrate this with some example. I want to start from the top there. So example, we can take two sets. We take two sets S and T. So let S be the set 1, 2, 3, 4, and Y and T be another set with elements, say 1, 2, 3, 4. So the Cartesian product then S cross T will be this collection of points. We shall have 1, 1, 1, 2, there are many, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, then 4, 1, 4, 2, 4, 3, and 4, 4. So all this collection represents the Cartesian product of S and T, with S given as that and T as that. Now I can describe a relation between S and T so that I consider the relation S is less than T. Supposing I define my relation R as S is less than T. Let me continue here. So we define a relation R by S is less than T. Let's say that is my R. S is less than T. Then I can represent all those pairs that represent my R. Then I still want, I want to squeeze that relation here so that we can compare. Then we have there. Then my relation R will comprise of these ordered pairs. The element from S is less than that from T. So those pairs will look like, I'll take all those pairs from S cross T that satisfy the first element is less than the second element. First is less than second. So I will circle with a different color the ones that satisfy my relation R. These two do not satisfy. 2 is less than 3, 2 is less than 4, 3 is not less than 2, 3 is not less than 1, 3 is not less than 3, 3 is less than 4. 4, all the others do not satisfy. So my relation R will comprise of these pairs. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. 2, 4, and then sorry, this one more that I'm leaving out. Then we have 3, 4. So those are the pairs that are found in R, where R, the relation R is S is less than T. So, and you can see all these are subset of S cross T. You can find all of them in the Cartesian product of S and T. So in this case now, I can make another remark. Sorry. I can make another remark here. Since we have obtained all the members of R from S, then we can conclude and say that indeed R is a subset of S. R is a subset of S cross T, of that Cartesian product. So that is in agreement with what we have said earlier. And then now, supposing I want you to find the domain of R. What will be the domain of R? Domain of R, as R, when R is defined this way, is a set of all first entries in the ordered pairs. So the domain of R will comprise of elements 1, 2, and 3. And the range of R, let me have it down here. The range of R will comprise of the set of all the second elements in those pairs. So we shall have the range as 2, 3, 4. So depending on how the relation is defined, you can obtain its domain, you can also obtain its range. Another example, supposing now in the same set S and T, suppose now we vary our R and now we use a different relation, say the equals, the equality. I hope you can recall what our S and our T was. And now I want another illustration here where let R be the relation S is equal to T. Remember our S was the set 1, 2, 3, 4. T was also the same set 1, 2, 3, 4. Those are our two sets. S is equal to T. This is capital T. So then, the relation R will comprise of ordered pairs XY or small s, small t, such that S is equal to T. That will comprise my R, which we can write as, where S is equal to T, I will have the ordered pairs 1, 1, 2, 2, 3, 3, and 4, 4. Those are the pairs that will satisfy the relation R. And now, what is the domain of R in this, with this definition now? Domain of R is the set of all first elements. So will be the set 1, 2, 3, 4. And the range of R is the set of all second elements. So we have again 1, 2, 3, and 4. Suppose my R now to be less than, I want, we already had the less than. I want R to be, I'll give you an exercise where now I want R to be the relation R to be greater than, S is greater than T. So as an exercise, obtain, now this is an exercise. The domain, let me just use the notation, domain of R and range of R where R is this relation. The relation ST such that S is greater than or equal to T. Is greater than or equal to T. So you will obtain R, that is the relation R that obeys this property. And then now I want you to obtain the domain and the range of R. Our relation R here is S is greater than T. So the pairs are such that the first element is greater than the second element. So, and remember my S, the two sets have elements 1 up to 4. So we are saying that S is the set 1, 2, 3, 4. T is the set 1, 2, 3, 4. And now my R is defined as ST such that S is greater than or equal to 4. S is greater than or equal to 4. So equality is accepted and now greater than. So my ordered pairs will look like this. S, I can have 1, 1 for equality. I can have 2, 1. I can have 2, 2. Sorry, yes, 2, because I am strictly obeying the equal to or greater than condition. 2, 2. Then 3, 2, 3 will not belong here because 2 is less than 3. So I need where the first entry is greater than the second one. So 2, 3 will not work there. 2, 4 will not. 3, 1. 3 is greater than 1. So we have 3, 1. 3, 2 will also belong there because 3 is greater than 2. 3, 3, will 3, 3 be a member there? 3, 3 will belong because 3 is equal to 3. Now, 3, 4 will not belong there because 3 is not greater than 4. 4, 1. Then 4, 1 will belong there. 4, 2 will belong there. 4, 3. Again, 4 is greater than 3. And also 4, 4 because 4 is equal to 4. So those are the pairs that I will have in my R. Those are the ordered pairs we have in R. 1, 1, 2, 1, 2, 2. 2, 3 will not be there because 2 is not greater than 3 and 2, 4. Then 3, 1 is okay. 3, 2 is okay. 3, 3 is equal. It obeys equality. 3, 4 will not belong there. 4, 1, yes. 4, 2, yes. 4, 3, yes. 4, 4 obeys the equality. So those are the members we have in R. And now from this, the domain becomes D of R is now the set of all first elements. So we have 1, 2, 3, 4. The domain, not the domain, the range of R is the set of all the second elements. The set of all the second elements. So we have 1, 2, 3, 4. So again, 1, 2, 3, 4. So there we are. I want you to now obtain the domain and range where the equality here is not accepted. So that one I'll leave you to do on your own. So can call this one, sorry. For 2, we can say obtain the domain of R and range of R where R is the relation ST such that S is greater than T. So that one you can do it as an example.